All right, the question is regarding the oxidizing agents and reducing agents. Why oxalic acid is a weak reducer and chromate is such a strong oxidizer. And so, what did you find online for that, Matthew? Electronegativity?
So we're talking about electronegativity.
Yeah.
Like a roundabout kind of logic.
Electronegativities are often used to argue things like acid-base strength, redoxability, stuff like that. You know, electronegativity makes sense if you're looking at something like fluorine. You know, fluorine is a very powerful oxidizer because of its very high electronegativity, right? But the problem with electronegativities is that we have such a limited table. We only have what's called the Pauling's table of electronegativities. In the Pauling's table of electronegativities, the fluorine has a 4O, right? And everything is lower than that. But the electronegativities change depending on things like the charge, like fluoride. Does fluoride have an electronegativity of 4.0? This is a favorite question I like to ask in Chem 1A. No, would you expect it to be lower than or higher than 4.0? Why? Why would you expect it to be lower?
No, would it be higher?
Would it be higher? Why would you expect it to be higher? What is the definition of electronegativity? I know it's been a while since Chem 1A, but what is the definition of electronegativity?
Ability to attract electrons.
Ability to attract electrons. So with fluoride versus fluorine, which one would have a stronger ability to attract electrons? Fluorine versus fluorine plus. Fluorine plus would have a much higher electronegativity. But we need a table. Well, you know, what specifically is electronegativity of fluoride? What specifically is electronegativity of fluorine with a positive charge? Do we have that data? We don't have that data. And so if they're using if you saw it on the internet, they might be using electronegativities. That's very, very possible. But if you look, you know, the Pauling's, when you look at the electronegativity tables that are available out there, Pauling's is like the elementary school version of electronegativity tables. There are the electronegativity tables out there that are much, much more thorough. And so if you're using those electronegativity tables to argue about oxidizing, reducing, that's okay. You could do that, but we don't have those tables. We just have the Pauling's tables. And so what's probably better than using electronegativity tables is to use what? What do we use to get a gauge of if something's electron rich or electron poor? There are electron counting systems. What are the electron counting systems? Do we use the octet? Sometimes. Do we use the formal charge? Sometimes. Do we use oxidation state? All the time, right? We use oxidation state. And so here the oxidation state is -1, the oxidation state is 0, the oxidation state is +1. So obviously this one's going to have the highest. It's the same element. This is going to be ranked like that. And so, why, this probably some people already know, and I know some people had already written this into their lab report. And so, you know, that's always good to read that. In the rough draft that I looked at last time, some people just said, you know, oxalic acid is a weak oxidizer, but they didn't explain anything beyond that. You know, I wanted some kind of detailed reasoning why. Some people didn't even bother saying, you know, oxalic acid is a reducer. They just concentrated on chromate, and other people just didn't say anything at all. They just said there's a redox reaction. And so that's typical in a report like this. You know, you'll have the full spectrum from the people who can talk a little bit about it, from the people who talk nothing about it. You know, and so anyway. Oxalic acid, chromate, we can see why chromate. What is it, dichromate or chromate? Chromate? either is going to have a very high, this, a lot of people look at this and say, it's already got electrons. Why does it want more electrons? You don't look at that because that's the net charge. We look at the charge, the individual charge on the atoms. And so why is chromate such a powerful oxidizer? Yeah, because of this. This is plus 6. Plus 6 is a very high charge. Is it really plus 6? No. It's not really plus 6. That's just what we call the oxidation state. It's a parent charge. But it's not going to lose all 6 of its electrons. If you look at how many electrons can it lose, well, it can lose 4 of these D and 2 of these S's. That's a total of 6. And then it's isoelectronic with argon. And so this is what we call the maximum oxidation state of chromium. It shouldn't lose any more than this because these are core electrons, which are hard to lose. And so this should be a powerful oxidizer. I mean, if you think about successive ionization energies, I don't know if you looked at the chart, but the 6th ionization energy in the chart in Chem 1A, it's going to cost you a huge amount of energy to do this. And so if it costs you a huge amount of energy, it becomes less and less stable, as it goes up in energy. It has a long way to fall. And so this is a powerful oxidizer. Carbon's interesting because carbon shows a rich redox chemistry. Carbon varies from plus 4 in things like CO2 and carbonate and others, all the way to minus 4. So these are the limits, the range, because carbon sits right in the middle here. And so if it loses 4, it'd be isoelectronic with helium. If it gains 4, it'd be isoelectronic with neon. So carbon can go either way. CO2 can't go either way, though. The carbon in CO2 is already plus 4. It's already at one extreme. So the only thing CO2 can do is be a oxidizer. And methane can't go both ways. Methane can only go and be a reducer, right? And so if we look at, what was it, oxalic acid? Where does oxalic acid sit in this range? And so oxalic acid is plus, this is minus 2, minus 8, plus 2, 6, plus 3. Plus 3 means carbon is more on the oxidizer end of the spectrum or on the reducer end of the spectrum. Right in the middle would be carbon, the element, which is 0. It's more on the oxidizer end of the spectrum. And so do you expect it to be a good reducer? No, but it can, because each carbon is capable of losing 1 additional electron to go to plus 4. And so the arguing that comes from this is just that it's already got a relatively high positive oxidation state. To pull an electron off a carbon with plus 3 is going to be more difficult than pulling an electron with a carbon at 0 or pulling an electron with a carbon at minus 4, right? And so it's just going to be more difficult to ionize this carbon than any of these. And this one's going to be extremely difficult because we're going to be pulling a core electron off that. And so this is why that oxalic acid is a weak reducer. If you go back in the video, I talked about this stuff, at the beginning, and there you can get more ideas for your paper. But that's along the lines that I was looking for, just kind of reiterating what I said in class. At the bare minimum, you should be able to reiterate what we covered in class, And then to be exceptional, to be a standout, then you add something to it, for the future. And so, like, people are looking for standout papers. Standout papers, you do something, do something beyond what was talked about in class. The papers that don't stand out are the people who don't even reiterate what was talked in lecture or discussion about this, They just kind of summarize it and keep it too brief. And so you want to do that at a minimum. For me, I kind of expected that because, you know, a lot of stuff is lost, you know, between lecture and notes, and so usually if you people who just reiterate everything that I said regarding this, you know, will have a good paper, you know, like an A paper. The people who go beyond that will have extra points. Okay, and so it's just being able to recall what was said and then just add that in there. But I think looking at the rough drafts from the last round, I think only 2 or 3 groups talked about this and not in great depth. To give you an idea. And so then I thought, I'm going to collect another draft. See how this goes. All right, other questions? Talk about. Yeah.
For number 16 on the practice test,
Uh-huh.
you have to use a combined KSP.
What was it? Can you read out the question out loud, somebody? Number 16.
So it's calculate the solubility of calcium sulfate at a pH of 3.
Calculate the solubility of calcium sulfate at a pH of 3.
Yeah.
And the question is,
Knowing that it will be a simultaneous reaction of these calcium sulfate dissolving and it says there's a formation of sulfuric acid, like the first proton of sulfuric acid would go and combine with the sulfate part of sulfuric acid. You have to do combined equations that you don't have to do simultaneous reactions.
yeah, well, one thing, you know, all these can be solved simultaneously. And so, yeah, you could do simultaneous, but, you know, whether you get an answer or not, different story. But where did you hear about sulfuric acid? I mean, when I think of calcium sulfate, I don't see any sulfuric acid in calcium
Because
sulfate.
it's being dissolved in an acidic solution.
Because of the pH. So you're getting the hydronium with the sulfate and it's going back.
Hydronium with sulfate does not form sulfuric acid initially. It forms hydrogen sulfate. Okay. Well, it depends. Does it meet the criteria for combined? What is the criteria for combined?
KSP small and
KSP small and
K is large.
K is big, so it meets the criteria. And so yes, you could use combined for that. Okay, other questions? Yeah, this is the method that was introduced in this chapter is the combined method, you know, which makes things nice because we just have one ice table to solve. Well, was that pH the initial pH or the equilibrium pH?
He said that he was gonna.
Did I say about? Did I talk about this yesterday?
He was fine. He said
Ah, it would be the final pH, the equilibrium pH. All right. Any other questions from the homework or Chapter 18 stuff?
Are we trying to get the lab reports today? Qualitative?
Yeah. Do you have the qualitative? A bunch of you have already turned it in, so I have some of these qualitatives.
And the lecture?
What I really wanted was the. What I really wanted today was the rough draft and the qualitative.
What about this one?
The Le Chateliers, you could turn that in too. But the Le Chateliers, if you have it in your notebook, it's okay. You could just leave it there. I'll check it off later sometime.
No, he said that you can just use the, you can show it. I thought that we had to do a report separate. Is this a qualitative?
Just put them in the same file. It's all right. There's not much room.
Which one's the qualitative? I thought only the rough draft was due today.
Do you want the homework
Qualitative
also,
analysis.
or?
Yeah, the homework is fine. Throw it on the different file. Homework? Just the qualitative and the rough draft can go in this file here.
Can I bring the rough draft at the end of class because
Yeah.
I couldn't print it out?
All right, that's fine. No, don't turn in their notebook. If you don't turn in your lab notebook today, I don't have time to check it off today. I'll look at it some other time. Your observations.
Professor? I didn't have the lab, the equations for the ones I did find in my solution. If I write those out and turn them later, it's gonna be kind of late. I got all the equations for the ones
You found, but you didn't.
Yeah,
No,
for
all
the
right.
ones
This
in my unknown that I did find, I forgot to write those in. I didn't know this was due today actually. So
yeah. Turn it in. All right. From yesterday, we did this lab, and we did 2 experiments. From experiment 1, we're going to generate a plot, but you know, the first thing is time 0. What was time 0? What would you say time 0 is? When the first drop hit, or when the last drop hit, or when the middle drop hit? Time 0, you know, what did you add last? The crystal violet? When you add the crystal violet, when the first drop hits the solution, does it start reacting? Yeah. But if you did that, there are many drops still left in the pipette. And so if you waited until the last drop hit, then you're too early or too late. And so what you have to do is you have to figure out where the middle is, right? To kind of average out those errors. Where the middle is. And so in the middle of dispensing the crystal violet, was it in the cuvette, and were we measuring the absorbance of CV plus? We weren't, were we? In fact, there was a time delay, wasn't there? There was time delay. And so the real time 0, we didn't record because we didn't. I asked if there's a stopwatch, I think, but there was no stopwatch. And so we're actually missing the first part of the data here. But that's all right because the curve should, the curve should be apparent. Was it linear? Was it linear? Or was it kind of curved? It was curved? A little bit of a curve? All right. And so we started collecting data here. Went down. Regular intervals. But what we're missing is just this beginning part here. But based on the shape of this curve, can we still determine if it's first order, second order, 0 order? Yeah. And so that's okay. We can live without this first part of data here because we can still determine it. And so from experiment 1, we should be able to figure out what the order is. And what the order is we're going to make 3 plots in the computer lab. We're going to just take the absorbance of the crystal violet. The absorbance of the crystal violet is directly proportional to concentration. So essentially this is the concentration. How the concentration is changing. Then what we're going to do is we're going to take the log of the absorbance and plot it against time and see, if that's more or less linear. And then the inverse of the absorbance. And so we'll generate 3 plots. Depending on which plot is most linear, that'll tell us the order with respect to crystal violet. Experiment 2 is the same reaction, just different concentrations. And so experiment 2 should just confirm this, you know. And so again, at our real time 0, this is going to be our time 0 from the instrument. So again, when we start the experiment, there's a time lag before we introduce the sample here. And so this is the instrument time 0. And we'll get the absorbance of the crystal violet. And again, we might see a curve here. And so we'll just repeat this. So we'll plot the absorbance, we'll plot the log of the absorbance and the inverse of the absorbance and see which plot is most linear. Both experiment 1 and experiment 2 should agree. Now, if you're getting conflicting results, then something's wrong. And so if experiment 1 says first order, then experiment 2 better be first order too. All right, but this is just the order with respect to Cv+. How do we get the order with respect to hydroxide? How did we do that? Did we do a third experiment? No. What's the difference between experiment 1 and experiment 2? Yeah, experiment 2, essentially we just doubled the hydroxide concentration. And we left the crystal violet concentration the same. And so that technique is called the method of initial rates. With the method of initial rates, we see if we double the hydroxide, did the initial rate double, quadruple, or stay the same? If we double the hydroxide and the initial rate stays the same, then it's 0 order because hydroxide doesn't impact the rate. If we double the hydroxide and the initial rate doubles, then it's first order. It's linear dependence. If we double the hydroxide and the rate quadruples, then it's second order. But what is the rate? Well, the rate is the initial rate, right? Where is the initial rate in these graphs? Is the initial rate, at which 0 is the initial rate? The 0 for our LabQuest system or the real 0 when the reaction really started? It's the real 0. Here would be the initial rate and here would be the initial rate. But we have a problem. The problem is, how do we determine what the initial rate is when there's no data there? Well, if there's no data, then can I just go ahead and use the instrument times 0 for my initial rate? I'll just use my instrument times 0. Because the instrument times 0, well, did you time it? Like when you mixed it, and did you time it from the, actual times 0 and the instrument times 0? Is this block of time the same as this? So let's say it took 30 seconds or a minute. Let's say it took 1 minute, and so 1 minute we started here, 1 minute we started here. Did we do that? Should we have done that? Maybe we should have done that, right? Maybe we should have started both at 1 minute, but it doesn't matter. That's the reason why we didn't time it, because after 1 minute, do you think the hydroxide is still double after 1 minute? Would the hydroxide still be double? Yeah. Well, think about it in this way. If you started off with, well, maybe it is. You'd have to think about it. But there are other problems with doing the initial rate. One, we don't have the data here. Here it's going to be doubled. And the other problem is this. You know, the initial rate, there's a lot of potential error in determining the slope here, isn't there? Because what you're doing is you're only using the first maybe 2 data points in determining the slope, or maybe you're just trying to eyeball the tangent. But if you only use 2 data points, then you have to really worry about, you know, what do we have to worry about? Error. We really have to worry about error. And so for this lab, what we're going to do is we're going to try to use all our data for the method of initial rate, not just the beginning part of the data. And so to use all of the data, I don't want to talk too long here. We do this. This is the modified version of the method of initial rates. In the method of initial rates, we usually take the bigger rate, let's say 2 over rate 1. 2, maybe I shouldn't use 2. I'll just say rate bigger over rate smaller. This is the way we normally do it. Rate big, put the bigger rate on top, the smaller rate on the bottom. And so figure out which one has the faster one, experiment 1 or experiment 2. And then we know that the rate for the bigger one is just equal to K times these concentrations. And so I'll just call it, the bigger I'll call B. And so the Cv plus and the hydroxide, B. And the smaller, we'll call Ka, and the Cv plus, and the hydroxide, A. So one thing is the 2 Ks. The 2 Ks are going to be the same thing, right? And so those normally cancel, but we did one other thing. We made the hydroxide so big that it's fairly constant. And so here, with the large hydroxide concentration, we're going to combine these 2 terms and make a new constant. We'll call it K prime B. This is Cv concentration over K prime A. This is Cv concentration. But the Cv concentration is, yeah, the Cv concentration is the same in B and A. We didn't change that. And so this just gives us K prime B over K prime A. So now, what can we do? What are we after? Well, we're after the order dependence here. And so we don't know what the Cv is, so we call that M. And we don't know what the hydroxide is, so we'll call it N. forgot to throw out those in here. And so, looking at this, let me rewrite it like so, that K prime for B over K prime for A is going to equal this. The hydroxide concentration for B to the N over the hydroxide concentration for A to the N. Now, which one was faster? Experiment 2 or experiment 1? Which one seemed to take? Was it 2? All right. And so what we're going to do here is we're going to take K prime for 2 over K prime for 1 is equal to this. It's going to be the hydroxide concentration for 2 over the hydroxide concentration for 1 raised to the nth power. Now the hydroxide concentration for 2 is double the hydroxide concentration for 1. So we're going to just have 2 times the hydroxide concentration for 1. That's hydroxide concentration for 2 over the hydroxide concentration for 1. And so the hydroxide concentrations cancel, and we get 2 to the n. And so this is equal to 2 to the n. Now, we can figure out what n is, by just using some math. But how do we determine K prime 2 and K prime 1? So the way we do that is by the graphs. We figure out which graph is linear. If it's 0 order, which was linear. If it's 0 order, then actually this is for CV plus. Then the absorbance versus time plot is going to be linear, and K is just the negative of the slope, K prime. If it's first order, then a plot of ln of the absorbance versus time will give a K prime value equal to the negative of the slope. And so what happens here is if we're taking the slope of the line that fits this, what it's doing is it's averaging all our data, not just 2 points. And so in this way we could use the entire data table to determine what K the slope is. If it's second order, then 1 over the absorbance versus time will give us a straight line, and the slope is just equal to K prime here. All right, so that's going to give us this. We just figure out which of these plots is linear, and then we determine, once we determine which one's linear, we just figure out the slope of the line, and that's our K prime value, the slope. But K prime is not the same thing as K. To determine K, from experiment 1, we get that K is equal to K prime 1 times, divided by the hydroxide ion concentration for 1. Because K prime 1 was equal to K times the hydroxide ion concentration, so we just undo that and just get K. From experiment 2, K is going to equal K prime 2 divided by the hydroxide ion concentration in 2. And then the best thing to do, the 2 K should be the same. The K primes are not going to be the same, because K prime has hydroxide concentration, and here in K prime 2, we double the hydroxide concentration. And so we get K average K average is equal to, K from experiment 1 plus K from experiment 2 divided by 2. That would be our K average. And so, doing this, we should be able to generate the rate law for the crystal violet. The rate law is going to be K average times the crystal violet to the M. We get M by just looking at the plot, which plot is most linear, that tells us the M. And the hydroxide, we get the hydroxide by using this modified version of the method of initial rates. And so we'll plug in the numbers here. All right, any questions on this? This is what we're doing in the computer lab next week. All right, I'm going to stop here. You can take a break.